So, hi everybody and welcome again to the Raspberry Pi live coding, hacking, whatever stream. First of all, as usual, please let me know in the chat if you can see and hear me. Last time you couldn't really hear me, so I hope this time it's better. And I will take this opportunity to say thanks to Hackaday, which helped spread the word about today's live stream. And hey Nekati, I can see your message in the chat, so I hope this means that I'm loud and clear and everything is perfect. And perfect. So let's go straight into the business. I will share my screen. You should be seeing my screen now, and here is me in the corner, small and little. And oh, that's my own page. And let's see what we did last week. So last week we implemented a bunch of new instructions, and then we tried to start a code from different places. So we loaded a boot ROM into the flash, and then into the, not really the flash, we just loaded it into the emulator, and then where was that? Changed where is that? Get memory. Yep, we changed the code so that it reads from the boot ROM if we are trying to read from a relevant address, and we implemented a bunch of we tried like running the code from different places and seeing how it works. And we also found a really cool ASCII art in the source code of the Pico SDK. But I asked people on Twitter about this ASCII art, and it seems like they removed it. Not only they removed it, there is an issue. I think no, I didn't prepare that SDK. So there was a pull request. I think that was number 10, where they removed this cool ASCII art, but they also made some change to the boot sequence. So what we did last time was using the previous SDK. So this is the pull request, and it's pretty big. You can note, yeah, this is so sad that they removed this cool ASCII art. So in order to save like 10 or 20 minutes today, I just, where is that? Yep, I just, no, not this one, the other one. Yeah, this one. So I just checked out the latest code, and I rebuilt the SDK and all the examples. So now we have them ready, and we can start looking at the disassembly file. This is the updated disassembly file. And you can see like there are a few changes. First of all, we have a dump of the boot stage 2. Before that we didn't have it. We had only, I don't know if we have a copy of this somewhere. Maybe, yeah, I think we had last time, but we probably closed that file. Anyway, we don't need that one. You can see like we don't have the disassembly, but at least we have the assembly dump here. And yeah, actually, no, this is like past the boot ROM. So we can see the hex values, but we don't have any of the hex of the instructions. And then let's remove the terminal. We can see that below that there is so it used to be that the code started at this address, and I think last time we even where was that? Yeah, we even jumped to this address to skip boot stage 2. But right now this is no longer an option because they changed things. They shifted things around, and now there is the vector table here. So that's what that pull request is about. Move the vector table to the beginning of flash image. So we will have to adapt and change strategy. And I don't know if you remember, but the first D word of the vector table is the initial stack pointer. And I think we sort of not here. We sort of simulated that at some point, like jumping and setting up the initial stack pointer. Not sure, but anyway, that's the initial stack pointer, and then the next entry number 1, is the reset vector. So this is where the code starts executing, and remember we need to remove the LSB, because that's like it means the high bit there, the LSB, means it's ARM thumb mode, which is always true for the CPU, so we can just ignore it. Anyway, so this is the reset handler, and this is where the code starts. And if I remember correctly, we spent a lot of time last time on this sequence of instructions, understanding what's going on there. And I think they have changed, because I don't know why, but maybe we don't have to worry too much about it, because if we just we already implemented this instruction, so maybe things will work. I don't know. We can have a look at the new boot ROM. So if we let's close this one for a moment. Yep. So if we take a look, there are still like 5 different files like we had before. And the thing is, now they have those includes. So instead of like repeating the code, this one actually doesn't have includes, but some of them do. Are these the latest ones though? Oh, let's see. Yeah, there is no ASCII art, so this is probably the most updated. So yeah, so there are like a few includes that are probably some common functionality, so they refactored it. I think what's going on now is basically this one, I think, is the one that is included in the images that are built by default in the this disassembly file, in this hex file. And now we have to decide whether we want to try to execute from the beginning, like we started doing last time, and execute this boot to sequence or not. And in order to do that, let's just take a quick look at the instructions here and see if we already know how to handle most of them. So this is where stage 2 boot starts, and we have push, LDR. I think we have all of those. I'm not sure about BICS. Let's see. BICS, I think. No, we don't have it yet, so we'll need to take care of BICS, or just maybe we can skip it for now. And then a lot of STRs. I think we have those. I hope we do. I think we have at least one variation of STR, or maybe no. Yeah, we do. Okay, cool. Moves, okay. A lot of interesting instructions. Yeah, so I think we will just try and see what happens. But before we jump into that, let's first of all update the hex files with the ones that I built today. So I think we are working with the UART right now. Is that correct? Yes. Hello, UART. So let's copy the latest and greatest with the updated vector table and everything. And now I guess if we run that npm start, it will no longer work. It will no longer actually it didn't work last time as well, but I think let's see if this is still where main is. So by the way, I would love to know in the chat if there are any people who haven't seen the previous streams and are like new here. So maybe I will say a few words about what we are doing and where we are at. So just let me know in the chat. That was main. So yeah, so now we see main is in a different address than it used to be. And that's exactly why we are like, we want to start executing the image from the very beginning, from this boot to start, because we don't want to care about that. We don't just want to get any arbitrary image and run it. And so let's for starters, let's just set the address to to the beginning of the flash, and just run it and see that it doesn't work. Yep, it crashes because it probably we didn't implement some instruction, or probably the instruction here or this one at 24. And we will take a look at this in a few moments. But first of all, there is something exciting that happened this week. Some guy, I think he might be here on the live stream. His name is Tony, and Tony, let's see, he sent us a pull request and he added a new feature. I haven't looked into this pull request. It was sent like 5 hours ago, but he added the BICS instruction, which I think we said we need to implement last time. Let's see. Yep, we wanted to add it last time. Like we concluded that we needed to add those instructions so we can get like the remaining part of allow UART to work without the boot stage 2. Now we added boot stage 2 into the mix. So this is like it just probably did this for us. I'm going to take a look at that in a moment. But before that, this Tony has actually also started working on his own RP2040 project. It's not an emulator. As you can see, it's a Python project, and it's a disassembler. So I think it could be useful for us actually to take a look at, why does it have an, I haven't looked at the code, but it seems like it reads from the boot ROM, and then it just has like this logic to disassemble all the instructions and print them, which is kind of cool. So good work, Tony. And now after we had a look at your disassembler project, let's take a look at your pull request. So let's see what you have changed. So I think this file is not really interesting. This is like VS Code configuration, and then there is a diff 000. I think you may have reformatted the entire file. Okay, so the diff is not very useful here. We may be able to get a better diff from Visual Studio Code. So interesting why there is such a big diff. Like it shouldn't be so different. I mean, I guess this line appears exactly the same. Maybe there is something with the new lines. I don't know why GitHub doesn't recognize the diff correctly. And then we have the same problem here, I guess. Yep, basically it couldn't calculate a diff correctly for some reason, probably line endings, but it's hard to tell. Okay, and then okay, same problem here. Okay, so normally I would probably request changes, and I think that should be pretty trivial to fix those diffs. I'm not sure, but in this case, we know what we are looking for. So basically, he said that he implemented the BICS instructions, so we can just take a look at the relevant pieces. So just look for BICS, and we can see that there is a test case, and then there is like this is the implementation with some debug logs, and there is this opcode and test. So we'll just copy them to the project and then say thank you in the commit message. So let's go to the opcode. Where is that? Assembler. Yep. and start doing the diff manually. Now there might be a better way to like check out a branch locally and do whatever, but I think this is like the fastest way to get going. And as you can see, like my auto formatting adds these parentheses, and that's because I'm using a tool called Prettier, and there is this configuration file here, but I guess I wasn't too optimistic, so that's my bad. I didn't set up the repository to automatically run this code formatting on every commit. You know what? Let's just do it real quick now, because I'm really glad that people here are contributing, so I want to make it easier for you. So basically there is a tool called, where is that? Yeah, Husky, which can not a dog, a tool called Husky, which can automatically run Prettier on every commit. So Prettier Husky, let's Google that. And there is, here is how to do it. Pretty quick, when you want an entire file formatting on your change staged file. Sounds good. So let's do this. Installing the packages, and then there are so many options here, but yeah, let's start with this one. We can change it later. I think this is pretty quick, is good when I just want to use Prettier. Then these are good when I want to use other linting tools, which is also a good thing to have, and we'll probably set it up at some time in the future. Anyway, I installed this Husky and Prettier pretty quick package. I also need Prettier, I guess, because right now it's not installed as a dev dependency of the npm package. And okay, and we need to add this piece of configuration. Just copy paste. Yep, and so as soon as we commit it, which will be in a moment, we will have Prettier automatically run and format any kind of code that is being, of JavaScript code, I guess, I hope, that is being committed. So going forward, whenever people will contribute new code, we won't have this issue with the new lines or whatever, and the formatting will be consistent. So we'll get the parentheses added here for clarity. Anyway, so let's set up Prettier on every commit, or maybe run Prettier on every commit. Cool. Yep. Yeah, that looks legit. And I think, yeah, push, we are good to go. And now we can continue with this new edition of the BICS. So we have this opcode BICS, and then we have, where was the pull request? Here it is. We have the test case for it somewhere here. Yeah. So no, assembler spec ds, bx, so right here, and add a import. So yeah, so first of all, this is like a register number, so I don't like using this magic number, so let's just create a constant for it, so it will be clear that this is like the register number. And I only figured it out because Tony wrote, where was that? Tony wrote it in the test that this is BX LR, and I know that LR is one of the registers, so but yeah, it's a good idea to define a constant for that. And then we know that this should probably be assembled to this. Let's just double verify it. So there is this online disassembler tool. Sorry, Tony, I'm not using your tool. This is just a bit faster. So I used it a lot when I developed the AVR disassembler. So I just paste the code and hope the Indianness is correct. Set the architecture to ARM whatever. and force stamp mode, and probably Indian. Yeah, so yeah, that's BXLR. That's the correct opcode, so we know the test tests the right thing and the test passes, so this probably works. I'm not even going to verify against the datasheet. And now we can close this one. We have to copy the implementation. So let's start with copying the test case. Yeah, copy paste programming, the best way to write code. BX after all those other B's. That was not this one. BX. That's the implementation. Where is the test case? Yep. So in the right place, copy paste programming and import. Oh, cool. Here, Tony created this constant. So let's recreate it again. That was, I think, 14. If no, we'll figure it out very soon. And we see that the test case doesn't pass, but fortunately, we don't have to write a code. Someone else already did. Where was that? That was here. And yep, let's add this piece of code, and then let's see what it actually does. It doesn't seem too complex, but it's nice to have it done for us nevertheless. Oh, it's failing because we still don't have the... Yeah, let's do it just now. Open them side by side, RP2040, and where is those instructions? BL, now BX, and it's not BX register, it's BX instruction. Oh, that's, yeah. Is there like BX which is not a register? Let's see. BX. Where is that? BX. So we ended up looking at a data sheet. Yeah, it seems like there is only BX register. There is, so we can just keep it BX to keep it simple. There are no, and then there is like this temp value, which is unused. So we can probably delete it. And I think this looks legit. Let's just have a look. What does this do? If condition passed, BX write PC. So let's see what it does in a moment. So it copies the values of RM, which is just, what is M? Probably, no, not sure. Okay, so if M is 15, then unpredictable. So if we are copying PC into PC, then the result is unpredictable. And then there is like BX write PC, RM. Interesting. And these bits also need to be 0 always. So maybe we should also ascertain that. That would be 7. Just to make sure they are 0, as the datasheet says. Oh, not that way, this way. Yep. Okay. 1, 2, 3. Yeah. Not sure why this is in parentheses, but I guess this is okay. Anyway, let's see what does BX write BZ do. BX write PC, branch 2, if current mode handler. Okay, we may have to deal with that later with the mode handler and exception return. Else, what is espr.t? Probably whether we are running in tab mode, because it's copying the LSB, and it should always be 1, but I guess we can ignore it for now in the simulation and assume that it's 1, and then we just branching to and setting the LSB to 0. So that's BX writing PC. So yeah, we take, okay, so I can already spot a bug here because we need the PC to be 0. I mean, not PC, the LSB to be 0. So probably n not 1. And then I don't think this should change LR. Does it change LR? This doesn't change LR. And then that was BX. I don't see anything that changes LR here, right? So this seems like a bug, I guess. Okay. Yeah. And now the test fails because we haven't changed LR. What did it change LR to? Point to the next instruction. So I think you might have confused with BLX, which is also, I think, yeah, BLX is writing to LR. So yeah, we'll probably get to that soon. But yeah, BX doesn't seem to do anything with LR. So we can remove this whole thing, and then the tests looks fine. So yeah, thank you, Tony, for contributing this BX instruction. And now with this new instruction, let's see if there is anything. Like, I think this is a crucial instruction because this is how you return in ARM code. So now all our function calls, they are implemented, but not the returns. They weren't implemented, now they are. Maybe our code will do better now. No. It's always good to stay positive though. Okay, so yeah, it has this instruction that is not implemented, and this instruction that is not implemented, and a bunch of instructions. And then at this point, I'm not sure what's here, but it's reading from an address that doesn't exist in the flash. So probably something here, kind of calculation that went off. And we can see like there was the code was executed pretty much linearly. So maybe we'll make it a little bit cleaner. This prints the PC as the instructions execute. So let's add this print so we know what this output is. So yeah, it's pretty much executing linearly, and then at some point it took a branch, it went this way, and then at this point it blew off. But the thing is, and that's why we didn't want to debug the boot 2 last time, we don't have the disassembly for that, which is kind of annoying. But maybe we can try our luck with the online disassembler. So first of all, let's copy this into an empty file and then use this cool feature of Visual Studio Code to just, reformat this as a proper hex dump. And we may have to shift byte around because of Indianness and stuff. But if we do, we can also do that pretty quick with those quick editing tips. Okay, and we pasted it, and let's see if this doesn't look legit. We probably need to swap the bytes or something like that. Let's try it with the first instruction. So no, I want just to reverse the order, I guess. So oh, maybe I can just cheat and tell it it's a big Indian. Would that work? Yep, it seems to have worked. Cool. So I'm not sure if it's legit, but let's just try to see if it matches the code on the boot ROM, and if so, oh, there is even a call graph here. Cool. Even though there isn't any graph here, there is no much code here anyway. Yeah. There is one branch that goes to D6 probably, but I don't think we went to that far away, or did we? No, we went to from 30 to BC. So let's see if there is anything interesting at 30. 30. LDRH PC. Okay, so that disassembly might not be the best thing after all. It might still be messed up, even though we swapped the bytes. Let's take a quick look at a stage 2 bootloader and see if it makes any sense, or let's force it to make sense. So the first thing it does is push LR and then LDSR3 something, and that's not what we are seeing here. So let's go back to Little Indian, and then let's just take the first number and make sense out of it, and then we'll figure out the rest. So this is the first one. Okay, so this one, and then let's try, I guess we should just shift those two and those two. Yeah. Yep, so yeah, so that's what we need to do in order to get this to work in the let's just undo everything we did here. So we need to get this thing into this thing. So I think this one comes from here. Yeah, we just need to reverse the bytes. So let's do another quick editing trip here and just you know, reverse the bytes. So this one goes here, and then this one goes next, and this one goes here, and then we remove those addresses. One, too much. Yep, and we don't need this. And okay, we are ready to paste it into the disassembler, and now we can see the complete disassembly of the bootloader, and we see there is like some kind of loop here, and yeah, we can see this branch at 30 exa. Can I download this, or maybe I can just put it for now side by side with this console output? So let's see what's going on here. Oh, Tony explains that oh, I see. Tony explains what happens with the pull request. So it's but it seems to be the same directory. Yeah, it seems to be the same file, but probably something messed up. Never mind that. I still really appreciate this. Okay, so we go, now we can see the code, so it's much easier to debug. How do we get rid of this? Perfect. So yeah, so it does all of this, and then which one is unimplemented? C. What is it? C. BICS. So let's take a note. We need no copy paste here. Yeah, but how do I copy paste this? Not so friendly. They're like a download. Never mind. I'll just type it again. That would be easier. So stage 2 missing instructions. So we are missing BICS, and we are missing also let's see. So all of these are happily implemented. Read blah blah blah. 24. What's a 24? STR. This one. So I think we have STR, but maybe not this specific variant. That was 24 STR. Oh yeah, R1, R3, R2. So we probably have this one, which is with an offset and not 2 registers. It shouldn't take too long to implement. So this one is also missing. And then let's see, at 30, what's 30, 30, 30, 30? We take this branch, and we should, because it's BL, so it's a function call. We are calling a local function. And let's look at the source code for the boot ROM to figure out what this function is. So we should have BL, read flash sreg. Okay, so I guess that's the function. Let's see if there is moves and CMP right after it. Maybe I will make the font. What did I just do? Maybe I will make the font a bit larger, so it's a bit larger, so it's easier for you to see. But now, yeah, it's not the greatest tool, but it's free, so whatever. Yeah, so BL moves CMP. BL moves CMP. Yeah, it looks like this is the branch that we are. This is the function call that we are taking. So we are going to read flash sreg, and where is that defined? In another file. Okay, and it just does something in a loop. It's doing something, storing something into a register, calling wait SSI ready, doing something else, and then doing this pop. And we just have to make sure that this code execute. We don't really care about what it does probably with a flash. Maybe we just needed to return the right value, but let's see why we get thrown off by this instruction. What's at AC air conditioning at AC? So AC is, yeah, we can, this is probably the branch from C2. Where is C2 BL? So this is probably this branch to wait SSI ready, and then inside wait SSI ready we execute the first instruction, which is probably this push. Not sure why it puts the label here, because we are branching here, but probably because there is a loop. Anyway, it executes a push, and then the next instruction would load something from R3 plus 40. So that's where we fail. We are loading something from R3 plus 40. Let's look at the source code. So R3 seems to be pointing somewhere, right? We are storing R0 into that place, and then we are calling. So if the store works, why doesn't the load works? Let's see what wait SSI ready. So yeah, it loads from the same address. So store is working, but load not. Interesting. So let's figure out what the code expects to have at R3. Where is that? R3. So it's probably the code that calls this one. R3. We also, where is this initialized? Yeah, it's, oh, so yeah, R3 just has the, should have this value pads QSPI base, which is this magical address. Okay, so let's just print the value of R3 and see if it gets thrown off at some point. Otherwise, not R3, MCU.registers3. Okay, otherwise we may have another bug. Let's see. So yeah, R3 is pretty strange at this point. So yeah, at the beginning it's like that address as we expected, but at this point it changes. Let's see why. PC18, what's it? PC18 moves, oh, interesting. Moves R10, so maybe, oh, yeah, no. Interesting, there seems to be a bug here, right? Wait a second, what's it, 1A? Yeah, like none of those instructions should change R3. Maybe this one at 16, but it seems to be, oh, maybe that's the instruction at 16 that changes it, and we just, you know, printed the value in the next iteration. So yeah, what's at 16? What's there? So let's check the source code. So probably, yeah, XAP SSI base. Where is that? Yeah, that seems to be the correct value. So it has what it should have, this value. And okay, R3 it doesn't change, and we are doing a bunch of writes, or at least, yeah, we are doing a bunch of writes that don't fail to this address. But yeah, I see why this might be problematic, because this looks like a flash address, and it's not. So we probably don't have any code that looks at flash writes, but we definitely have some code that handles flash reads. So we are trying to read from this address. As long as we are writing there, what happens is that where is those? Yep. So as long as we are writing there, it's calling this method, and then if we don't have, like, if we don't know where this should go, we don't have like writing to the flash, only to the RAM for now, only to the RAM and to the SAO address space. But if we don't understand this address, we just look for a hook, and if there is nothing that handles this write, we just silently ignore it. But with reading, we do handle this flash start, and basically, if the address is in this range between this value and the SRAM start, which this magic address certainly is, it's in this range, we assume that this is a flash read, and then we just read from an invalid address from the array, and it throws an exception. So I think what we should do is just look what the datasheet says about this address. But I guess this is something that is related. We have seen that XAP is like something that is related to the flash, and this is probably some kind of registers that don't know what's SSI, but where was that? Yeah, but we should probably just not treat these addresses as, where is that? Yep. Yeah, SSI, synchronous serial interface, QSPI, overview, blah, 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 blah. Not interesting, really. But yeah, I guess there are like some registers that control those SSI. Where are we anyway? Why don't we see this in the index? Yeah. So 4.10. Yeah, there we go. Yeah. And yeah, and then we have all those registers that configure the SSI, probably that's the flash. And we should definitely not use, like, this should be this address should be ignored by us for now until we handle that. But we can see that there is like this XAP no alloc base and no cache base. So I guess even lower addresses can be ignored by us. Let's see if they are mentioned in the datasheet. Yep, they are, but obviously no explanation about what they do. Yeah, so the XAP register started base of address. Yeah, so I can say it's pretty sure to assume that any address above this is not a valid flash address. So let's go with that assumption for now. So instead of flash end address and flash end address, and feel free to correct me if this is wrong and we should set this lower, but for now it seems like it might do the trick. Okay. And Tony is writing that he found the exchange in the name is not about exchanging register. Oh, BICS may switch between thumb and not thumb mode, but it's not relevant for this MCU because it only has thumb mode. So thanks for explaining that, Tony, to me. Okay, let's see what happens now. Yep. Okay, the code does something interesting. We have those invalid reads, which is what threw us off before, but it seems like we have to deal with them because I see like it seems like this is a sequence of instruction that is repeating, so it probably expects something to be there in order to proceed with the boot sequence. So let's take a look at the code. I think that was in this wait SSI ready. So it reads R1 from this address, and then it's SSI SSR TFE bits. So yeah, BQ1B that goes back. So it does two tests. It tests these bits and these bits, and I think it wants to see that they are 0. Not sure about that. What are those bits? So this is bit number 1 to 3, transfit v4 empty, and this is bit number 1, SSE busy. So I guess we should make sure those bits are 0, because I guess right now, no, it wants, let's see, it loads this value, then it does bitwise and BQ if the result is 0. So those bits probably need to be set, if I'm not wrong, in order for it not to take the branch. SRTFE and busy, so bit like the number 1 and number 4. So let's make sure it's there for, so this is the memory address it's reading from, and let's go to the run link, and yeah, we can close this one for now, and we can start by adding. Actually, this is like part of the microcontroller implementation, because this is going to be useful for every program. .set, and we'll shortly replace this with constants. Let's just see that it works for now, and just return, 5, which is 1 or 4. Okay, I will just use the constants. That makes more sense than. And then this is this, yeah, const and the other one was this. Okay, and this where is that magic value? This one is basically this offset, which is this. So plus that base address, which was, I don't remember. Let's take a look at that was here somewhere. XAP SSI base. Yep. Yeah, maybe at some point I will just copy all the defines from the SDK instead of having to manually copy them when we need them. No, we don't want to export it, just to have it defined, and then XAP SSI base plus, where was that? Here. Cool. And let's see if this works, if this finally boots. Okay, something different happens, I guess. It goes AC, AE, B0, B2, AC, AE, B0, B2. So that's another loop, I guess, we are stuck in. Let's see what's there. So AC, AE, B0, B2. AC, AE, oh, it's the same loop, isn't it? So yeah, maybe we need those bits just to be, oh, yeah, of course, bitwise OR instead, logical OR instead of bitwise OR. You should have told me that. Okay, let's see. Okay, so now we get to B6, B8, and then we look back. So we got a bit forward, bit 6, B8. Oh, so it fails the second test. Oh, wait a second. What happens here? Moves one test. Oh, this is branch not equal. So we actually want that bit. The second test, where was that? Yeah, that's branch not equal. So yeah, we want the busy bit not to be set. So it's not busy, just TFE. And let's run this again, and voila, where did we get? Still the same. Did I not save or something like that? B8. Oh, wait a moment. This instruction isn't implemented, and then we just get thrown off. What's at BA? BA is BA. Where is BA? Pop. Okay, so that makes sense. And I see that this pop is actually doing a cool trick. They are popping pieces, so that's how they return from the function without wasting space on you know, on another BXRL instruction. So at this point, I'm pretty sure we will need it shortly anyway, because every time we push something into the stack, if we don't pop it, then the flow blows off. So let's do pop. Let's take a look at thanks Tony for the pull request. We are done with it for now. Let's take a look at pop, and I guess it shouldn't be too hard since we already have push. So this is the encoding. You know what, let's disassemble it. Let's start by writing the disassembly for it before we jump to implementing the instruction. So push, we don't have one for push because didn't have this mechanism in place when we started with push. Okay, so it fits here. And let's just take this pop as a reference instruction. Where was that? That was here. So BD03. Okay. That was pop, and it was pop with R01 and PC, and we want it to be BD03. Okay, so opcode pop, and yeah, I don't think we have something that encodes. Oh, we do have something that encodes an instruction list. So let's use the same syntax. So pop. So that would be R0, R1, and PC, which is R15. We'll need to define a constant for that. R1, and this is PC, R15. And then let's implement the decoder for it. Go away. Assembler, and we can remove this for now. Okay. Did I copy it? Did I not? Okay, opcode B. That's not what I wanted to do. Opcode pop. Second is BNE. Yeah, thank you, Che Guevara's. That's true. Thanks. Okay, and just like LDMIA, it takes register as number, and then it does its magic. What's the magic look like? So let's take a look at the datasheet. Datasheet, where are you? Pop. So all of this niceness. And this should be shifted by 9. And then there is P. What is P? P is probably if we pop PC, right? Registers 15 equal 1. Yeah, I guess this means that PC is this one. So maybe we'll just change the syntax a little bit to make it easier for us. Instead of this, let's do PC, or let's just call it P boolean, and then we have register list. Oh, funny, I'm editing the same file in two different windows. That wasn't what I wanted to do, but anyway, so this one has PC, and then also those two registers. Yeah, they call it P here. Cool. And then so that's P. Whatever. That's shifted by 8, and then just the register list. And does it work? We need to import, and yes, it passes. So we have the assembler, and then we can go on and implement the instruction. So yeah, let's just copy the test case for push and do pretty much the opposite. So popping, and we are popping PC, and then that was R0 and R1. Actually, let's just, do the exactly reverse thing of what we did here. Like we are popping R5, R0, and R6 because we push them in the test case for push. In a line, and then instead of this niceness, that should be opcode pop, and we are PC is true, and then we are using these registers, and instead of this, we did this is like what we expect to have. So these are the expectations that we will have. To equal, and then they should be equal to those values, and then we just need to push those values to the SRAM. So yeah, let's also we want the to make sure that SP, so if it starts here, I guess it should end up here. That makes sense, just doing the reverse of push, and then yeah, we can just change those to assignment. So just that's nice because we have push, so we can just sort of reverse the reverse all the expectations and the initializations and expect it to just work magically. I don't know, I hope we're popped from the stack correctly, and we are popping PC, not LR this time. Cool. So now we have the test case, and it's, I don't know if it's any good. I mean, it makes sense that it will be good, but let's just implement pop. Where is push? That was a bit long, but I guess pop is pretty similar. So let's just copy paste, and I hope we are not shooting ourselves in the foot by copy pasting too much here. Okay, so if this is like the opcode, okay, and then opcode and 8, and we need to turn it into a boolean, not a number, because TypeScript has types, so it actually cares about these things. And then let's look, and that's pop, not push. And let's look at the algorithm. So what do we have here? Register list, bit count registers is less than 1. Like if there is nothing set here, then it's unpredictable. We don't have to worry about unpredictable. Okay, and then address equals SP, and yeah, it seems to be pretty straightforward. Just where is that? We don't need this bit counting, I guess. Address equals SP, and then for I0 to 7, we already have that. If registers I is 1, so that's probably checking, this is checking that part. Then RI equals reading from address, so registers, so pretty much the reverse of this one. So this dot read, and we are reading from address, cool, and address plus equal 4, and then if P, yeah, we can probably just copy this condition like we did with push. So if this is true, then we need to load, yep. So we need to load into this .pc the value that we had in address, yeah, and then sp is 4 times bit count registers. Interesting. Oh yeah, registers is like everything, right? So basically we could just guess to this, and then just sp is, yeah, that's sp. Okay, it passes, perfect. I don't have to test anymore. I mean, it looks great. It's all green. Let's just run the code and see what happens now. I love TDD. Okay, so we got somewhere. Invalid read. We are, where do we go? I think we got back from this branch. So it means we managed to return to 34, 36, and then something happens. 30E. What's it? 30E. 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 So we got this. We did this branch. We got back, and then at 30E we have another call to this function. What's that? Let's see if we can spot that in the source code. So that was the first BL. Where is that? I wish I had syntax highlighting here. So we went to this function, we got back, now we jumped to this function, and I guess we should just you know, run a few more instructions and see what happens now, because it doesn't seem like it's in some kind of loop or anything like that. Before we do that, let's just you know, remove those R3 debug prints, and let's just go 100 instructions. Yeah, let's get crazy and see if anything interesting happens. Yeah, so it goes somewhere, and it goes even further to 40. What's it? 40. 40, that's the last branch, and then it goes again, and then it goes back into until 50A. And what's at 50A? Probably another branch, this time to this. Let's try to find it in the source code, movs R5. And what happens next? So 50A, it goes to this function. Oh, it continues, but then it goes back to 50A. So there is probably some loop here. Yeah, I can see this loop at 62, 80, 58. Yeah, 62, go back here. So there is some loop here, and I guess we need to get through this loop in order to keep doing this boot to whatever it's doing. So let's see. So I guess this is this this loop. It seems move R5, move R1, test. Yeah, it seems to be reading from a specific flash register, and it wants to see that it gets the value 1. So this is the flash register it's reading from, which is this register. And where is read flash sreg expecting the value to be? So we need this register to contain the value 1 in order to be able to proceed with the boot. So read flash sreg, I think we visited that function before. Yep, read flash sreg. So R3, discard the first byte and combine the next two. Interesting. LDRH is the IDR offset. So yeah, so we are probably writing 2 bytes to this. So we are writing, but what does combine the next two means? I only see they are like loading. Interesting. So we are writing the value of R0, which is the status read CMD, and then it reads the result from the same address. What's STIDDR0 offset? Okay, so data register 0. And let's take a look in the datasheet to figure out what it means. But first of all, we don't need that. Let's create this constant. So what does this one do? Datasheet. There you go. No help about that, huh? Okay. Yep. DR0. And what does this do? First data of register of 36. Okay. So there are 36 registers, but what do they do here? Like, is there any explanation, or are we just left in the dark? Okay. Never mind, let's just, we know that it writes something there. Specifically, it writes, where was that? I think this one. Where was that loop? Yeah, this was the file. Yeah, so it writes there this CMD read status, and it wants to get 1, and CMD read status is defined as 5. Okay, so we'll just you know, create another flash hook. So if somebody is reading from here, yeah, we need to do 2 hooks. So this dot write hooks. So plus, that was, how did we call that? S something dd. Yep. So if somebody is writing there, let's define. We'll probably refactor this into a class that will handle all this XAP stuff. But for now, let dr0 equals 0, and then if somebody is writing this magic value, then if somebody is running this value, then we set the dr0 to 1, tell put stage to boot that we think wait a side, that was here, that we that write completion happened or maybe we completed a write. Okay, and then when we are reading from this, we can just return this value. Yeah, I'm not very proud of this code, but we'll refactor it once we get everything to work. Okay, let's see if we get past this loop. Seems to get past this loop. We get into 60A. What's at 60A? And there seem to be no loops here, right? Don't go back. 53, 60, 60A. 68, 60A. Yeah, it seems legit. Let's see what's at 60A. So 60A, 60A. Yeah, we are past all the loops, and we just need to keep executing, I guess. So let's keep executing. Run blink. It's actually running UART, but we'll fix that later. Okay, npm start. And ooh, what happened here? Interesting. So, oh, that's cool. That's cool. So you see this address? This is actually, I think, the bootloader going to the actual program. Let's see if this is true. Where is this? Where is this? Where are we? Where is this? Whoa. Where are you, hex file? Here we go. So what's there? Yep, it went to reset handler. So yeah, we managed to get past the boot stage 2, and now we are just executing the program from the very beginning. That's so cool. And interestingly, there is some instruction here that goes to 0, and I guess that means that something is off. I'm not sure yet, but let's. So first of all, since we got out of the bootloader, we don't need this disassembly anymore for now. We can just work with the program. And yeah, BXLR. So we implemented that, but for some reason this function returns to the wrong place. How bad is that? Like, there is this datasheet and something calls it. And then my guess is that the stack pointer isn't balanced, and then it contains 0, and then we just sort of restart or doing something really bad. And there is a bunch of missing instructions, but the first thing I'm going to do is just to do this. If mcu.pc is less than this value, like if it's less than the start of the actual code, if we are in stage 2, or actually no, only if we are inside our program code, then I'm going to print PC. So basically I'm going to just ignore not print all the noise that we have from the bootloader. We still have like all those reads, but at least we don't see all this long list of instructions that is executed. And then we can just see the flow here. So we can see that, yeah, that's not interesting. We can see that we go 1F6, Yeah, it seems to be pretty linear. So why do we return to 0? Let's see. Let's take a look at the code. So this is the reset handler, and it branch. Okay, there is a BL to data CPY, and that's a 206. Where does that happen? Yeah, and then 2 there and there. Interesting. So there is this BL. And then inside data CPY, we have an invalid value in the link register, or BICS doesn't work correctly. So it's either BL, BX, or I guess, what is BCC? One of those instructions is messing up, but I think we, words that R2 and R3, yeah, they are loaded from somewhere, but I guess 204 and then 206. So yeah, this doesn't even execute. Like, it goes here, it skips this branch because it gets here, and then things get messed up. So I think the best thing to do is just print LR and see what happens here. So let's do that. LR, and just let's see where it blows. Anyway, I'm super happy we got past the bootloader, and I'm pretty optimistic. Yeah, we might be able to get this program to run beginning to end today. Okay, so interesting. LR seems fine. It seems like LR is fine. So yeah, probably something with BICS if LR is fine. BICS LR. Let's check the implementation. So yep. What is that? Oh, my bad. It should have been OR, because no. Yeah, that's fine. We wanted to switch that bit off, but I guess we are not reading from the correct register here in BICS, because there is no way in the world this can give 14, which is the value of LR. So maybe we should take a better look at the datasheet and check what we missed here. Yeah, okay, RM. Oh, yeah, this is 4-bit wide, not 3 bits. But here we are, so the shift is good, but we need to end it with F. So before we do this, let's just write a test case or fix the existing test case, so we don't get beaten by that in the future. So let's see BX. So in this case, how come it works? Oh, okay, so this is a good example, I guess, of a test case that is succeeding, but it's succeeding because of the wrong reason. All the registers are initialized to 0, so even though it reads from the incorrect register, like it did here, and returns the value here 0, it just reads from one of the other registers, this test still passes because it doesn't matter. It will pass as long as it reads from any register, because they are all initialized to 0. So let's fix that. Instead of really doing this, let's do something like this. And now we can see that the test fails. Now the test actually tests that it reads from this specific register, and we can see that it fails. And now we can fix this by, yeah. So we need to read 4 bits and not 3 bits. Okay, cool. So let's remove the debug print for, yeah, we can remove this debug print now that we have found the issue, and let's start running things again. And okay, we are, I think, in the same place, but now our 22E. What's it? 22E. No, previous one. Yeah, now we have I'm wondering why this time it goes into a loop. 22A, 22C, 22E. Yeah, it goes to this data CPY loop this time, and this is probably initializing the data section of the program. It sounds like that's what it does. And I guess if we just bump the number here, we'll get past this loop, but I'm not sure about that. Let's see. Okay, let's go really crazy and see if it ever gets out of this loop. Probably a lot of debug prints, but no, it doesn't seem to get out of this loop. It does seem to read from invalid memory addresses though. So I guess the reason is we haven't implemented STMIA, which probably also changes R2, and then we are comparing R2 to R3 and it's never equal. So we should implement STMIA 2C, STMIA. We already got LDMIA, so I guess that should be pretty easy to do. STMIA where are you, STMIA? So yeah, let's create the encoder for this. So it has RN and register list, and where is that? Assembler, LDMIA, STMIA, probably here. STMIA, and oh, we need the test case. Let's do the test case. Let's create a opcode first. We already did it. So STMIA is just like this. And I think it's pretty much the same encoding, right? And then the next 3 bits are RN. And then, that was super easy. Reusing code, that's so fun. But it's STMIA, not SDMIA. All right, and then let's write a test case for it. That was... Let's see, STMIA with, we had here R2 and R0, so R2 and cool, and that should equal this value. Okay, test passes, nice, and just for the sake of it. Okay, so we have the assembler for that, and now we can write a test case for the instruction. So I guess it will be pretty similar to LDMIA, so we can probably copy that. Yep. Probably here. STMIA R2. And from R0, whatever, and just, oh, okay, actually, let's make it similar to, yeah, to the LDMIA test case that we have. So we can reuse the same logic, I guess. So opcode STMIA, okay, ST, not SD. Okay, and then I guess, let's take a look at what this does. So store multiple, increment after. Okay. So store multiple, and then the base register, and this happens. A list of registers, and then if registers, and obviously we can't have all the registers, only the 8 lowest registers. So if it's 1, then what is this? Okay, so it's writing the register to the memory address and adding 4 to the memory address, and then we just update the register. So basically, if I'm understanding this correctly, then if we have this value in the register R0, and then we have okay, so we have those values in the RAM, in the registers. So if we have those values in the registers, so then we expect R0 to increment by 8 because we are writing to registers, and then the first one, R1, should be written, so expect this, and instead of get uint, set get at this address to equal this magical value, and then yep, and then we are missing a parenthesis here. So yeah, so we have the test case. Obviously it doesn't work because we even forgot to change the name of the instruction. We didn't implement the instruction, but we'll have it in a moment. Let's just make sure, yeah, the first register R1 is stored first. I think that's what the pseudocode says, right? We are going da 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 da, and address is incrementing. Yeah, seems to be pretty good. And then I guess for the, let's do it side by side like we like. And then where is LDMIA? We'll just copy paste. I think the logic is pretty similar. STMIA, where do we put you? Here, or even here before str. Yep. So this is STMIA, and then we need to decode it. So this is the opcode 11 and zeros. So that's the opcode. And then we have RN registers, and we have seen like they are the same in LDMIA, so we don't have to worry about that. And I think we need to do is just switch this. So instead of reading, we call this write uint address. We are writing the value of the register. And green, yep. Let's see if this means we got past this loop. One more instruction. I really like the rate at which we are like creating new instructions today. Okay, so let's go up to 500 and see if we get past this scoping loop. Hopefully now we will. Not yet. 1500. Not yet, even though it still doesn't complain. So either we copy a lot of data, either something is wrong here. Yeah, probably something is wrong. So we know this loop is like comparing the value of R2 and R3, so it will make sense to print them and see what happens there. We expect R2 to increment as actually we also expect R1 to increment, but STMIA should make R2 go higher. So R2, yeah, R2, and then the same. There is no MCU.R2, just registers 2, and then the same goes for R3. Okay, registers, not register. Cool. Let's run that and see what happens here with those registers. Okay, so yeah, R2 is, or one of them is totally off, and yeah, like this is, where is this? This doesn't look like a legit address, and this doesn't look like a legit. This looks like some kind of, I don't know. Yeah, let's go back a bit and see what happens before that, before they get thrown off. Yeah, so 200, 202. So this value is loaded into those registers in this address 202. So what happens at 202? Yeah, we are loading the value of these registers from here. And are there any unimplemented instructions before that? And yeah, they seem to be pretty off because they don't change after, right? So something is wrong here, because they need to eventually match, because this function, what happens here? R1 0. So if R1 is 0, there is this loop that happens. Otherwise, we go to datasheet.py, and datasheet.py expect those to eventually match. So what's the deal with that? Let's try to find this source code so we can figure out the logic there. So reset handler, there you go. So this is hang all cores except for core 0. I guess this is not a problem. And then we are doing this and doing this. So what is ADR? Do we have ADR? It doesn't complain about missing instructions, so I guess we are good. So what's the data CPY table? There is like a bunch of addresses here. Source, start, end. start end, source start end. So probably some kind of the list of the data that it needs to copy from probably from source into this place until it gets to this. So that's source is where it's reading from, and then start and then end. Yeah, I guess so. R1 will be source, R2 will be start, and R3 will be end. So maybe there is something wrong with where is that R4 coming from? Data CPY table. It should have the address of this data CPY table. Let's take a look at it. Yeah, so this is what it should load, and it obviously doesn't do it. So either we got what was that? Yeah, either we got this one wrong or this one, either ADR. So let's just stop here. So if this is PC, then we just stop so we can see the values here instead of having to scroll. So if mcu.pc is this, then just break. Okay, and then we should also print R4 and see what happened there. R4, and just for the good measures, we have this, I think R1. Let's see if R1 gets the right value. Why did it? Property doesn't exist. Oh yeah, uppercase PC. Thank you, TypeScript. Oh, Arbel, thank you. I also love seeing it taking shape. And Tony wrote something and removed it. I'm curious what it was. Yeah, let's see how we make it take even a better shape. Okay, so oh, whoa, R4. The value doesn't make a lot of sense here. It's like, where are we anyway? So this address, this ADR, where is that? ADR reset handler, no, here. So so in this address, after this one, R4 should include the address, should have this value, I guess, which is the data CPY table. So that's at 1FE. And where is 1FE? R4 doesn't seem to have. Oh, and we have this. Well, yeah. I don't know how we missed this before, but we are missing this instruction, and that's the problem. So is it ADR or add? I'm not sure. Probably add register and constant, and we are missing that. Do we even have an add instruction? It should be at the beginning if we do. We have ADCS and ADS, but we probably don't have this ADR or ADD or whatever. So let's implement it. ADD, so RRIMM3. And is there like another one? And there is ADDS. Oh, that's ADDS. So is there any ADD register? ADR is add with PC. Okay, thanks, Tony. Yeah, I don't know everything. Like I'm learning here a lot. Okay, so which version of add should we implement here? So PC plus immediate, I guess. There is ADR. Yep, here we go. So address to register adds an immediate value to the PC value, and then write the value to the destination register. And we don't have to worry about any flags, I guess. Then that's great. So that should be a piece of cake. So let's do ADR. So where do we assembler? So opcode ADR. ADR. It fits here. export function opcode ADR, and it only gets one thing. No, it gets RD and IMM8, and I think it will be pretty similar to this one. So basically copying this, and then next is RD. Missing one bit here. One. Okay, and that's RD and IMM8, RD IMM8, cool. And it's 0 extending IMM8. We should take note of that when we implement it. Anyway, ADR, so assembler spec. And let's implement the test case. So ADC, and then we have, what was that? ADR, or whatever. What did it look like in the source code? ADR R4 and something. Okay. ADR R4 PC plus. Okay. Yeah, let's probably this would be the right way to describe it, even though I should do it here, just to keep things in order. So that would be the opcode. Where is that? Where did you go, opcode? So this is the opcode. Okay, and then ADCS. No, that's ADR, and we are adding R4 with 82. And our 82, 40, 52. Our 4 is just like R4 is 4, cool. And then oh, okay, nice trivia effect. Nice trivia effect, Steve. Good to see you here, by the way. Okay, so it doesn't work because we still need to we have this 0 extent, so we need to shift it when we encode instructions. So that would be ADR. So before encoding it, we need to shift it by 2 bits. Shift right. Okay, and now the encoding works perfect, and we can write the test case. So that would be rp spec ts, and where is it? Let's close this window and go to the beginning, and ADR, where are you? ADR. It fits right after this ADDS. Yep. Huh. Maybe we should have done this as well in the assembler. Yeah, ADR fits right after ADDS, not before. That makes more sense, just to keep things organized. Okay, cool. And then the test case is here. So ADDS, ADR, and that was whatever, R452. So opcode ADR R452, and then we expect R4 to have the value of PC plus. So let's see. So the value of PC plus 52, but I guess it's like the PC after the update, so it's PC plus 4, like this nice align thing. So I think we had this align thing. We need to do something in addition for aligning it. We encountered it in the past, probably. Yeah, probably just adding 2 to it would be fine. I hope so. We'll have a look at that soon. Anyway, in this case, we expect the value of R4 to equal this plus 52. Let's do this hexa to make things prettier. And yeah, Tony says +4. Yeah, but +4 makes sense. We already add 2 here, so that would be +2 in the implementation. ADR, and let's just not sure if we should also if this align where is that align PC4 should also do some kind of alignment or not. If add, and probably add is always true, yeah. Okay, so ADR is 10100, so 10100, and then we have IMM and we have RD, right? RD, and then we don't need all of this, and basically registers RD is just how did we call that? This.pc probably. Yep, this.pc +2, or maybe opcode pc +4, just for the good measures, plus IMM32, so just IMM8 shifted by 2. Okay, and the test case fails. Let's see why. Where are we? What's the value of R4? No, of this thing. Doesn't print it. Okay. We needed hexa. Interesting. Yeah, I guess I should have accounted for that. But why is it 54 and not 56 if we are adding 52 plus 4? Something is... Oh. Yeah, interesting. Adding 52. And then I guess the shift is removing, so something is strange here. So this is PC and it's adding 52, but I guess if we take 52 and then shift it and then shift it back, yeah, there might be a thing with the thumb, even though yeah, so this all mumble jumble of shifts should somehow I mean the 2 is not encoded here in this instruction, so how comes? Let's see what the online disassembler says about that. I mean, this is the address, right? And this is PC. So let's do the math for a moment. No, it's not adding for a 52 decimal. It's just adding. So it's adding this instead of this, which makes sense because it seems like the 2 least significant bits are always 0. I'm just wondering, maybe it's just like the compiler says it's 52 because that's the difference between this one and this one. So that's what I'm trying to find out. So let's do the difference and see what it is. Maybe it's like the way the compiler tells us it's like this one plus 52, but actually the encoded instruction doesn't contain 52. So even though then our test would have failed, yeah, it probably has something to do with the alignment. So this one minus this one minus this one, 54. Interesting. So I guess this has to do with the alignment. So in practice, it goes 54 forward, which means it goes 50 from the next PC. So like PC plus 4. So it goes 50 from here. So this is actually encoded as 50, and which is the same as 52, but probably the compiler is writing 52 because whatever. The compiler is the address. This is relative to this address in the compiler for some reason. That's the only explanation I can tell about that. But anyway, so I guess then if this is the, let's make this make more sense. So then this should be 54, and then we are good to go. One last thing I wanted to double check is this thing about aligning. How does align work? I think I have like a deja vu, like we already checked it at some point. But just want to double check. The align value of an instruction in PC ended with to force it to be was the line. There is no difference. Okay, so we should end the PC value as was for us 4. So just for the good measures, let's end it with this. It shouldn't change a lot, but just I mean, it may change something, but just to be compliant with what it says. Did we do it somewhere else already? Yeah, we did it somewhere else already, this kind of alignment, so that's good. Anyway, this is implemented. Let's check what's going on with the code. If now, yeah, it seems like it works. R2, R3, it seems like the values here make sense. They are pretty much similar. Let's see if these are actual values from the table. Yeah, so this is like R1. It's, oh, yeah, it's close enough, but maybe it's the next one. Not sure. Interesting. Anyway, R2 and, oh yeah, this is the same one, and this one is for C and C0. Yep, it seems to be loading the values correctly. No, ARM instruction is not always divisible by 4, Tony, because this is thumb, so it might be like divisible by 2, but not 4 in this case. So, or maybe you are talking about thumb. Anyway, so in normal ARM, then yeah, that doesn't matter, but in thumb, this actually can make a difference. Anyways, seems like we're good to go with this pile of non-working code. So let's go back to run Blink and see if we can get any further. So no need for debugging, no need to stop, because we are optimistic that we can get out of this loop. And let's go much further. And let's see what happens. Oh, whoa! It got out of that loop, and now we are in a different loop. Interesting. 214. What's it? 214. BSS fill loop. Okay, so this is, I think, just storing 0, filling the data section with 0. All the I don't remember what BSS stands for. Yeah. So let's just keep running it further and see if it ever leaves this loop, and if not, we'll just print the values of the registers. Yeah, seems like something is also off here, because that's 22228. Oh, that's actually somewhere else. So interesting. So I think we got into platform entry, which, if I'm not mistaken, this is actually the place where it goes to, eventually it goes to, jumps to runtime main, init, and then main. But something went horribly wrong here. 228. What is it? 2228? 228. BKPT breakpoint. Probably. Yeah, it shouldn't get here. Something went wrong. We shouldn't have. Yeah, this is like just when everything finishes running. So either it worked and the program ran, but it shouldn't probably get there. Let's see where this got out of control. Actually, yeah, let's just stop the first time we get into this address so we can see what led us there. And so yeah, this 216, what's a 216? BSS field test. So then we should get here to 21A. And what's, oh, I know already, like we can probably spot it somewhere here, but I think we need to implement BLX because we don't have it and we use BLX here. So I don't know why this doesn't show up here. Oh, maybe we just don't run enough instructions together. Yep. 2 to 4 to, so yeah, we need BLX and then we can finally jump to main. But before we get to main, we also have like this small beastie runtime init that we should somehow manage to get through safely. So let's do BLX and then we may finally be able to get the entire program to get into main and execute. Maybe not. Let's do BLX. What does BLX do? So I think it's just like a combination of BL and BX. BLX register, branch with link exchange, blah, 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 blah. So this is the encoding and yeah. Okay. Let's do the encoding then. Assembler spec. Let's start with the test case. So BLX. So BLX, and that was BLX. Where was that? Yeah, BLX or whatever. Let's say R3, even though it's not the same place, is it? Where are we anyway? I disoriented myself a bit. I think we need to go to the first runtime init. Oh yeah, we went to that platform entry. Yep. So BLXR1. Yep. So BLXR1 should be equal to. Oh, thank you, Steve. So yeah, that's cool. Good idea to add a break instruction in case of not implemented. We might do it, but first I want to get it to work. So this encodes to this. BLX R1 should be a piece of cake to implement. So probably the same as BX, but with a different constant. Let's see, RM, and then this happiness. All right, and import it, and it should pass. Yeah, it passes amazingly. And then we can go into, we don't need you anymore, assembler. We can just write instruction. So BL, BX, and we have BLX. And wait a moment, we need a test case first. So spec and BL, blah, 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 blah. Let's do BLX. BLX, that was R3, I think. So the instruction is opcode BLX with R3. And then let's see, we have this PC, and we have an address in R3. So so yeah, so we first of all we need to put some address in R3. So RP2040 registers 3 equals, let's say we are BLXing to this address, whatever. And then after that, we expect PC to have this target. So yeah, just doing BLS write PC, which probably just copies the value to PC, but let's make sure. Yeah, branch to whatever with that bit set to 0. So similar to BL. So anyway, let's make it interesting. Let's make this one 1, and then we expect PC to have the same one with 0. And what else? So LR should have the next, yeah, just like BL. Yeah, I think we are good to go. Let's implement that. So if this is equal, where is BLX? BLX, yep. If this equals that, and then remove all the spaces, and yeah, just like here, all zeros. Then we have this RM, which is like here, 4 bits wide. Pretty much same as BX, except for that we also save the value of PC into LR. So like that, I guess. Yep, green passes. Let's see what happens with the code then. Oh, whoa. So yeah, it definitely got into somewhere like here, which seems that we are somewhere deep inside runtime init. LDR, STR moves BICS, B and E. So this goes here. So we are in this tight loop, and we have some instruction that isn't implemented. So that's probably why it doesn't really work. But I'm not sure. Let's see what's this address, BICS, and I think we had seen this BICS before. I remember something like, yeah, we needed it also for boot stage 2. About PC-2, what is that in the chat that you are asking for? PC-2? At least like I think the BLX works, like it got it into runtime init, so it seems like at least half of it worked. Maybe the LR part didn't. We'll know as soon as we get past this enormous runtime init. But you know, just for fun, we can add something like this. If this.pc or opcode this, no, that was opcode PC, right? So if opcode PC, where was that platform entry? So we are just going to skip this first branch, this runtime init for a moment. LR, no, LR is like, I think it should be the same as BL because it's branch, so you want it to return to the next instruction. Oh, yeah, I think you might be right about it's not PC-2, it's actually PC because we, yeah, so BL is like that's actually, that's a good spot. Thank you very much, Che Guevara, for spotting that issue. When you write the tests and the tested code at the same time, you might get it a bit wrong. So you probably saved us a lot of time. We want it to return to the next instruction. So if that was the PC, we want the function to return to one instruction after. In case of BL, it's 2 words, so it's 4-byte instruction, so it makes sense to set LR to this PC plus 2, but in this case it's just this.pc. Let's even see what it does here. So yeah, PC minus 2 is actually next PC, which is PC plus 4. It's a bit confusing, I know, but basically here this .pc is already this it's already with plus 2, and here it's already with plus 4, so that's why we do minus 2 here and we don't do this minus 2 here. So if we compare it like into BL, so in BL we can see that here we use PC, but here we use PC plus 2 because of this difference. A bit confusing, but hey, now the test is correct, the instruction is correct, and that part works. And yeah, I was starting to cheat, and then you corrected me, so let's stop cheating. What I was going to do is just, you know, maybe we can still do this real quick just for the sake of it, and then get back to the boring making this init runtime work. But we can do that like if mcu.pc, just skip this very specific BL to platform entry, so just skip this instruction. So if this happens, then mcu.pc plus equals 2. So just cheating, so we can finally see the UART output again, or maybe not so. We got totally thrown off by this. First of all, yeah, I guess the reason, like, we had this working before, we had main working before, is because we didn't have branch BL. So when we called main, then it didn't do all the USART initialization, and now it does them, and it probably get thrown off somewhere there. So anyway, my quick and dirty hack didn't work. Let's get back to work. Okay, npm start, and let's see what happens here. So we got into this loop, and we have this instruction which we already saw that is missing. So let's do that. We need it anyway at some point. BICS. What is BICS? BICS. Bitwise and complement and writing. Oh my, another Bitwise or something like that. Anyway, let's do this. Let's start with the opcode, assembler, no, not here, assembler, BICS, export function, opcode BICS. No, it doesn't take an IMM anyway, it takes RM and RDN, and number, RDN number, and then it returns this magical string of okay, 0 be this shifted by 6, and then RM and 7, right? That's only 3 bits. Shifted by how many? By 3, and then RDN 7. Okay, and then we can write a test case for that. So BICS. Okay. So code BICS, and how that it worked, R0 R3 R0 R3 0 R3 BICS should equal this very magical value. Okay, and it doesn't work. Interesting. What did we get wrong? BICS. Okay, first of all, it's not number, it's a number. Okay, and why doesn't it work? Oh, it should be bitwise or not end, of course. Okay, that's better, but still we get pretty different value. R0, R3, and this is the value. So Rn, Rm. So yeah, I guess Rn and so here it's Rdn. Oh, it's implicit probably, but anyway, it should be Rn and then Rm, and now it works perfect. So just Rdn, whatever. Okay, and now the test case. Let's see what it does and do it. So BICS, where are you, BICS? You should go here. BICS R0, R3. So R0, R3. And then we expect it to do something with the values, right? Shifted, what is shifted? Oh, well, okay, shifted carry, shift C, So, okay, so this is a bit clear. Basically, it does Rdn, the value of Rm. Not sure what we have to do with carry, but it's shifted by 0. Oh, carry is just taking the value of carry, so it's unchanged. And then Rn and not shifted, so Rn, Rd, it's the same one. So basically we are taking this register and doing AND with bitwise not, I guess. That's bitwise not, complement, probably bitwise not of the other register. Okay, so basically clearing the bits that are set in the other register. So in this case, it means that we want R0 gets R0 and not R3. So let's set it up. So our pre-registers R0, let's say it equals F0, and then or actually let's make it equal FF, and then R3 is just 0F. So we expect it to clear those bits in R0. So we expect R0 to equal F0. And obviously the result is not 0, so 0 should equal false. And it's also not negative, so negative, that's n should equal false. All right, let's do this. BICS. Okay. So, don't we have a test case for B? Okay. BICS. Yeah. And let's decode this. So opcode should be this nice thing. Right, and we should shift it by 6 if I'm not wrong, and then we have RM, which is just opcode shifted by 3 and 7, and RDN, so that's RM actually, dn, which is just opcode, and this, so the bits of opcode, and then we should just make this. But let me know. Oh, that actually doesn't work anymore, or maybe this way. Interesting. It used to work. Anyway, let me know in the chat if you can see. I think interesting. Funny. It seems like it broadcasted the no internet or something like that from what I'm seeing in the monitor screen. Anyway, yes, it's back now. My internet connection didn't like BICS, but I think we already finished that. Perfect. Thanks. Oh, this is cool. A cool way to see who is here with me. So I see Dominic for the first time. So hi, Dominic. Okay. So where were we? Okay. Oh. So let's just do another check for the setting a negative flag. So where were we? BICS. So this one happened, and then. Yeah, let's make something with a negative result. So let's say this is just -1, too many F's. And we are clearing, let's say this part. So the result should be this, but this time, not twice 0x, but this time it should be negative. And then let's just update the flags, this.n if. Okay, let's do 0. It's easier. 0 if and if we can actually do something like this. I don't know if this shouldn't be legal to write this kind of code, but whatever. So if result is 0. And then if result, and I guess we already got it. Yep. Okay. Yeah, we don't need this nonsense because I guess it's 32 bits already. Anyway, so yeah, so we got 0 and n comes before 0. So let's do it, keep it consistent. Okay, we have BICS, and let's see what happens next with BICS. npm start, and what happens here. Ooh, yeah, it throws us off again. How did we get into this? Okay, so we managed to affect the we don't need this anymore. Let's just write it into a file. That would be easier to navigate and see what happens. So we went where did we get off? So here something went really wrong, and there is like some instruction that isn't implemented there. So just before that, so let's see what's there. That was here. LDRH, yeah, we are loading something into R3 and then BLXing there, but we haven't implemented LDRH, so it's going to a strange place. And what does ROM funcs lookup do? It sounds interesting to see what does this do. Okay, it calls this function. Oh, whoa, this is probably doing something with the boot ROM because it's called bootrom.c. So probably calling some functions of the boot ROM. Interesting. Okay, so it needs LDRH, and I think it should be pretty similar to something that we already have, which is LDRS. I think we have it. LDRH, and that's with the register, right? LDRH register and immediate. So LDRH, no, I think that's LDRH immediate in this case, because there is RTRN and immediate, right? So RDRN and immediate, which is 0. So I think we have something very similar already. So we have LDR immediate, that's LDRH immediate, and I think they do pretty much the same, just loading Halfword instead of just a complete word. So again, assembler spec.ts. Okay, LDR. And we also have LDRB, so it should be super similar to that. Let me just mute my phone. Sorry for that. How do I do it? Do not disturb. Yes. Yeah, just my friend telling me that is getting off the stream because he's too tired. I can get it. It's like 11 p.m. now in Israel. And we'll probably sign off after this instruction as I'm getting tired as well. Anyway, LDRH, okay, LDRH, so it should be similar to this, probably just, yeah, IMM5, RM, RD, IMM5, RN, RT, okay, whatever you want. Oh, it's already RT. Cool. So just the only thing that changes, and let's do a quick sanity test. What was that instruction? LDRH. Yeah. So this should equal this. Oh, thanks. Thanks, Steve. Yeah, my family is already asleep. I'm setting the streams to the time where my family is already asleep, so I don't have to worry about not spending time with them. But thanks for worrying about that. So that should be R7, R3, R7, LDRH. Does it work? No, because we haven't declared R7. So let's do R7. R7 equals 7, and it passes, right? Yep, LDRH, and then the thing I'm really happy about, like now that we have got most of the basic opcode covered, it really goes fast when we need to add a new opcode. Like last time I think we added only 3 or 4 opcodes, and now it's like boom, 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 opcode one after the other. Okay, LDRB, so let's do the same with LDRH, and this time it's do this. Okay, so LDRH R3 R7 plus 0. Actually, let's make it more interesting. R7 plus 4. So LDR0, blah 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 blah. So R7 should have, let's say, this, and then SRAM 5. It's LDRH, and that's okay. So let's say it has this value, and then it has some nasty stuff after it. We want to make sure it doesn't load. It only loads the Halfword, so 2 bytes, so these ones. And then we expect R3 to have like 7766, because this is a little Indian, so those 2 bytes. And we just need to implement the instruction RP2040 LDR. Oh, we have LDRSH, which is probably very similar to LDRH. So let's just copy this and use this as a template. So LDRH, so we have the opcode RM, RN, and RT. I think this should be LDRSH register, not immediate. I think this is a problem. Let's see. So yeah, it's register. There is no LDRSH immediate, I think, anyway. Yeah, probably copy paste error. Anyway, LDRH, in this case, we do need an immediate. So LDRH immediate. So we have RN, RT. RT is, let's start with the opcode. So first of all, this is like 11 because we have 51001. Okay, and then we have RN, RT. So RN, RT are good, and we have IMM5, which is just 5 bits, so 1F, and then we have address is registers RN, right? Oh, we need to have the value 0 extended, right? 0 extend this. Okay, we'll do it in a moment. So that would be IMM 0 extend. We have a 0 sign extend. We need just sign extend 5. So this dot. Don't we have this something like that already? Probably not. Okay, this dot just IMM5, so we are going to sign extend it, and then this is the address, and we just need to do this without any sign extension, right? So we need to implement sign extend 5. Oh, we have sign extend 8 and we don't even use it. Anyway, sign extend 5, if value and 1F, then this and F. Yeah, did I do it right? I hope. Yeah, it seems to be quite correct. Okay, and this doesn't pass yet. Why doesn't it pass? It received 0. Let's see what happens. Okay, let's print the value of IMM5. It's 4, and let's print the value of IMM32. Should also be 4. No, it's not. Interesting. So this is wrong. Oh, yeah. I should just check this bit. Okay, so yeah, now we pass. Yeah, so this also means that I need to be able to encode for negative numbers. So I guess I wanted to do something like that. So IMM, and then just take the sign bit from IMM. Do we have like one with the negative number, just so we can quickly test this? Okay, not really, but we can do this with the disassembler. Anyway, so if this bit is if this is less than 0, then we just need to set that bit and then shift it by 10. So that's the sign of IMM5. Let's add a test case. So LDRH, and let's do like, let's say -4, and then -4, and it's, let's print it, check in the disassembler if it makes sense, and if it does, then the test case is good. Otherwise, we'll have to figure it out. 8F3B. So online disassembler. That was 8F3B, platform ARM, and for stub mode. Yeah, we need to. Huh? Isn't it supposed to be negative? Why does it I'm pretty sure there was a sign extension, or did I miss anything? Oh, it's 0 extend. Why did I? Yeah, now it makes more sense. So we don't need all this nonsense that I just added. No need for this nonsense. I hope we won't need it in the future. So it's LDRH, just IMM5. It's not sign extend, it's 0 extend. And then we also don't need the nonsense in the assembler. So yeah, just remove all this. Perfect. Okay, so we got LDRH, and as I mentioned, it's getting pretty late here. So let's just run it and see what's talk about what's next, and then we can wrap off, I guess. And we are getting into a different place. We are no longer executing invalid instructions. We are just reading from a memory address that doesn't make sense, or maybe it does. I think these are like boot ROM addresses, maybe a bit past the boot ROM. Let's see, did we implement reading from the boot ROM? I think we haven't, or did we? Yeah, we did implement unit 32, that's reading from the boot ROM, but it seems like our code is reading from the boot ROM and getting past the end of the boot ROM. Okay, so let's take a look here. This is like this loop where it copies a lot of data, and another loop where it initializes data, and then we get here and we start reading invalid places from the boot ROM, and I guess it has to do with this unimplemented instruction. What's here? Move. We haven't implemented move, and we also need to implement ends to be able to get past this. So yeah, so for next time, I think we also had like we were supposed to implement moves this time, right? Yeah, that was move, but to get through somewhere we were looking at last time, I think the bootstrapping code or something like that. Anyway, so yeah, we have those two instructions we'll need to take care of next time. Let's see if there are any other interesting instructions that are missing. So SBCS, let's write them down. SBCS. So we have this one, and we have ends, right? That was this one. We have this move, and tang. What's here? D2, SBCS. And yeah, I think the rest of them are probably just repeating the same ones that subs to C. I guess that's, yeah, so probably we have this loop that does something, and because we don't have this move, probably and this one as well, probably something yeah, there are a lot of moves here, probably something gets out of control and never finishes this loop. So yeah, so next time we have these three instructions that that's the same one. So there was this one, and there was another one, I think ends, that one that we haven't implemented yet. Probably bitwise end with short. Let's see if we don't have it. Yeah, no ends for us. Okay, so we need to do those, but first of all, let's commit. Actually, I don't see any. Oh, okay, let's commit it anyway. So yeah, so wow, we added a lot of instructions. So let's first of all, yeah, next time we need to implement. Or maybe even more more dramatic announcement, get past boot stage 2. Yep, or that was stage 2 boot. Okay, so yeah, implemented our new instructions. So we have ADR, BICS, DLX, BX. Thanks, Tony. Is that Tony with I or with Y? With Y. Thanks, Tony. And maybe we'll also mention the pull request. I think that was pull request 1, because I think that's the first one. And we have LDRH and pop and STMIA. So that's all the instructions that we did today. Cool. So with that, let's commit, and yeah, I think we can already remove this part to start right after boot stage 2. We don't need it. And there is this interesting part which loads, sort of simulates what the bootloader does, which is copying it to the SRAM. I don't think we need it right now. It might be needed later to, just emulate better what happens on the real chip, but for now we don't care about it. And we already implemented BICS, and I don't know about that one, but it doesn't matter. We don't need this. We get past boot 2, so we don't care about that anymore. Cool. So oh, we have this, nice, but I don't think we need this. We already have like this console log uncommented for debugging, so we can remove this. And assembler, yep, this one, and commit, yep. And as usual, I encourage you, if you feel like sending any kind of pull request, like we still have like a few test cases which could use a little bit of beautification. So please do, if you like Tony did, that really makes me happy. Or if you feel like implementing one of the instruction, I think move should be pretty easy. And these are, I'm not even sure what does, like maybe subtract with carry or something, but move should be relatively easy. So feel free to take it and surprise me before next week. And then I think next week we'll hopefully get this hello UART to work beginning to end. We might have to fiddle with some of the registers, and then we need to decide what to do next. And I think there is like, what's its name? This PP something. PIO, yeah. So we can take a look at simulating the PIO, or we can run MicroPython. We can try to get MicroPython to run on the microcontroller. I don't know. So feel free to let me know how would you like this to continue, if we should work on PIO, on MicroPython, once we get this bootstrapping to work finally, or maybe something else, like there are a bunch of peripherals. Maybe we'll also find that we need to do the timers, so delays will work. I don't know, we'll figure it out. But if you have any preference of what to work next, then just let me know. Oh, there is like some new stuff in the chat. Thanks, Steve. Yeah, so let me know. Just as usual, I will write the address of the Discord, so you can catch me throughout the week. So discord.walkwith.com/discord. So just there is a specific channel for the RP2040JS, so you can just catch me there and let me know what you would like to work, what you would like me and us basically to work on next. And that's it for this week. Thank you for joining me to this adventure, and see you again on next Tuesday. Bye bye.